We are now going to review the most famous CNN architectures. We start with the first CNN named LeNet, which was first designed in the early 90s. The original aim of this network was to classify handwritten digits from 0 to 9 in order to automatically read postal codes and bank checks. The general architecture of this network resembles closely the one we've seen before. Here there is one convolutional layer followed by one pooling layer. Then again, one convolutional layer and one pooling layer. Then a flattened layer is used and several fully connected layers are introduced at the end of the network. Let us see the specificities of this architecture. The input image is a grayscale image of size 32 by 32, so its depth is 1. Here you have a more compact representation than before, where we have omitted the kernels and we show only the feature map output volumes of each layer. The first layer is a convolutional layer which takes the original image as input and apply a convolution with a 5 by 5 kernel with a stride of 1 and no zero padding. Note that with these parameters, the spatial dimension of the resulting feature maps, which are of 28 by 28, are smaller than that of the original image. 6 such feature maps are produced, which is summarized by an output volume of size 6 by 28 by 28. Here the depth is the first coordinate. Note that the kernel has 5 by 5 plus 1 parameters, the extra parameter corresponding to a bias, a constant term. After performing the convolution, an activation function is applied element-wise. We will specify this function later on. The second layer is a pooling layer. When implementing a pooling layer, you need to set the type of pooling, averaging pooling here. The average is computed in each receptive field. The receptive field, here 2 by 2. The stride, 2. We talk about non-overlapping pooling since the receptive fields are disjoint. Contrary to standard pooling layer, this pooling layer contains 2 parameters that will be optimized during the training process, a weight W and a bias B. This is non-standard for current neural networks. As mentioned before, pooling layers usually do not have trainable parameters. Zero padding is not used with pooling layers since it would consist mostly to add zeros around the image, which is often done in the next convolutional layer. Since the pooling operates on each layer separately, we end up with the same number of feature maps, 6, with a spatial resolution divided by 2. The third layer is again a convolutional layer. Contrary to the first one, it operates on an input volume of depth 6. A specificity of this layer is that the convolutional kernels do not operate on the whole depth of the input. Instead, for each kernel, we set in advance on which feature maps it operates. This is represented in the table below. You can see in each row the input feature maps and in each column the output feature maps. The crosses mean that a given output feature map is obtained by applying a kernel on the given input feature maps. For example, the first output feature map is obtained by applying convolution on the input feature maps number 0, 1, and 2 only. This has several advantages. It is computationally more efficient than connecting every output feature maps to every input feature map. Less connections to optimize. Besides, you break the symmetry in the network. All output feature maps are not built in the same way, thus they cannot produce the same outputs. Nowadays, this is quite uncommon, and we would connect every output feature maps to every input feature maps. Indeed, the depth of the kernel is almost always equal to the depth of the input volume. What about the remaining layers? Afterwards, we apply another pooling layer. Then, we apply a flattening layer, which transforms the input volume in a set of values neurons. There are 400 neurons here, which is exactly the number of values stored in the input volume of size 16 by 5 by 5. After this layer, the image structure is lost, which just deals with real values that are no longer ordered. The next layer is a fully connected layer containing 84 units, and finally an output layer that we will detail afterwards. The general structure of the network is called bipyramidal because the number of feature maps increases along the network from 1 to 16, while the spatial resolution decreases from 32 by 32 to 5 by 5 to end up with scalars. This is quite classic for neural networks, the aim being to obtain many representations of the images, feature maps, that are simple, composed ultimately of one real value, in order, for example, to detect or classify the image.